Okay, so this is my lead into the video for those of you listening live, just to say everybody's watching this is for today's lesson, and we're looking at the 8A work. And if you are watching live, you're welcome to jump in and ask any questions you would like at any point. You can see the questions are there. This is our learning goal and success criteria structure that I'll be using with you for the next couple of years. So definitely worth using these. They're a great point of reference if you want to go through and just work out if you know everything you need to know. Definitely worth having a look at. But anyway, this is what I need to talk to you about today. It's basically just a run through what you probably already know. Maybe you don't quite recall all of it, or you're not 100% sure on the structures. But I'm going to run through some polynomials work. And 8A is really just a review and sort of hammering home some of those key points about polynomials that you need to be aware of in order to move forward and progress with this topic. So polynomials, as opposed to some other functions that you've covered, are functions that have only x to the power of numerical values. Now, there is a set of polynomials called power functions that might have fractional indices, like the square root of x and things like that. But really today we're talking about those whole number powers. So if you can see the OneNote, we're talking about this px and qx as my examples there. Got heaps of notes written around them, so have a read of those. But you have polynomials are set up so there's potentially a coefficient, a, b, c's, and d's, etc., and then x to the power of different numbers. And you've seen a lot of polynomials already. You've worked with linear functions in year 8 and 9. You've worked with quadratic functions in year 10. And you've probably also seen cubics in operation. And we're going to go beyond cubics a little bit today as well. A polynomial is defined by its leading power. So it's called a quadratic if the highest power is a square. And you've been through this before. If there's a cubic in there, well, then the polynomial is called a cubic, even if there's a quadratic component. And so just to give you an indication here, I'm going to do a bit of highlighting. Okay, this has got 3x to the power of 4. It's called a quartic. So that's a power of 4. Now, there is no cubic term. So I'm going to refer to terms. But you'll see here there is a quadratic term. So we have a quadratic term within this quartic. We have a linear term within this quartic, and we have a constant term within this quartic. But there is no cubic term. Now, that doesn't mean that we can't consider the cubic term. It's just the cubic term in this case is 0x cubed. So there is a coefficient to the cubic term, and this may be important in some structures. It's just 0x cubed. So we have coefficients. The coefficient of x to the power of 4 is 3. That's just the number in front. We also have a constant term. So you'll see this plus 3 at the end is referred to as the constant term. And so that's our general structure of a polynomial. Now, I've just cut and pasted straight out of your textbook here. So go back and refer to this if you want, because there are, as you can see in red there, some important pieces of information. So the number 0 is called the zero polynomial. And even if you have something like y equals 4, this is a polynomial. It's just a straight flat line, but it's still a polynomial because it's got a leading term, x to the power of 0. So the leading term is the one with the highest power, as we just talked about. So a cubic has a highest power of 3, a quartic has a highest power of 4. The degree of a polynomial is the leading term's power. So the degree of a cubic is 3. The degree of a quartic is 4. The degree of a quadratic is 2. A monic polynomial will have a coefficient of 1. So it's called monic, and you've probably talked a bit about monic and non-monic quadratics. It's not necessary language, so maybe you haven't heard that before. I know the textbook uses it a bit, but as you might remember, monic polynomials are a little bit easier to factorize than non-monic polynomials. And then, of course, the constant term we've talked about. So just make sure that you're aware of those pieces of language because they can come up in exam questions, and you have to be able to refer to those pieces of language. So common polynomials here. I've got a few. Let's see if I can recall all their names. I've gone up to cubics. So here we have a quartic. Now, there's no surprises in any of these. This one here is called a quintic. And so we derive a lot of our language from, well, firstly from Latin, but also we've got a little bit of Greek in there, a little bit of some stuff from Roman, but also some things come through from just famous cultures that have contributed to mathematics historically. So there could be influences from Indian mathematicians or Chinese mathematicians who historically have built this. So sometimes there's multiple words. So you see 5, pent means 5 like a pentagon as well, but in this case we use quintic. But here we sometimes refer back and we flip back to the hexic form. And you might call this one an octic, and this one a decic. Sorry, my writing poor there. So as we get further on, we get the larger ones there. The syllabus says to us that we have to be able to, you have to be aware of and be able to refer to polynomials with small integer degrees. So there's no indication of what small is. Is small 10? Is small 20? Well, we've kind of taken, as a group of Queensland math teachers and from guidance from QCAA, that when it comes to small, we're probably talking more like 4 or 5 as the highest leading ones. And in terms of the maths we're going to do in Chapter 8, really even 4 is pushing the friendship with some of that. So you're probably going to be doing a lot of cubics. And we are going to be spending a lot of time with cubics over the next few lessons. So here's a couple of things. Polynomials can be added, subtracted, or multiplied exactly as you would expect. And I've got my first example here. So I'm going to just flip my screen down flat on the surface, which means instead of seeing my face, if you're looking at me, you're going to be able to see the roof instead. And I do apologise about that, but it's much easier to write. So we have px plus qx. I've defined px and I've defined qx there. Px plus qx is equal to, and I'll do it out with the full range of workings, 7x minus 6, that's my px, plus qx, 2x squared minus 1. I'm going to add those together, I get 3x cubed, because I'm collecting like terms, plus 2x squared, plus 7x, and then minus 6 plus negative 1 is negative 7. That's my px plus qx. Px minus qx, again as you would expect, 3x cubed plus 7x minus 6 minus 2x squared minus 1. This gives me an opportunity to just go through with you and make sure that you are reminded of the fact that when you're subtracting terms like this where there's brackets involved, you have to be a bit careful. So of course we still get our 3x cubed, and then we have negative 2x squared, so it's minus 2x squared, and then we still have plus 7x as our only linear term, and then we have minus 6 minus negative 1. So we've got a double negative there, and that actually comes out as negative 5. So there's my subtraction, and then we've also got our multiplication here. So that becomes 3x cubed plus 7x minus 6 times 2x squared minus 1. And this just becomes a bracket expansion. So when I do a bracket expansion, I'm going to always do the distributive law. So what that means, I'm going to distribute every term in my first bracket over the second bracket. So I get 3x cubed times 2x squared minus 1 plus 7x times 2x squared minus 1 minus 6 times 2x squared minus 1. So when you're, in your earlier years of learning maths, you probably learn about particular FOIL comes up a lot. FOIL works fine if you've got a 2 terms times 2 terms set of bracket. It doesn't work so well when you've got 3 terms in this first bracket. The distributive law that I've just applied always works. Distribute the first bracket over the second one. And of course, some of you will be able to do this probably a bit quicker than I'm doing it, but that's okay. I'm going to do it this way anyway. So I've got 6x to the power 5, this is working, minus 3x cubed, and then I have, so that's my first one, plus 7x times 2x squared is 14x cubed, minus 7x, and then I've got minus 6 times, 2x squared is minus 12x squared, and minus 6 times negative 1 is plus 6, and so there's my second one, and there's my third one. So I'll just be careful to include that negative inside because the 6 is positive. And now I can bring those like terms together. That's my only x to the power 5. It's my leading term, so I'll leave it there. And then I've got an x. I've got no x to the power 4s, but I've got 2x cubes minus 3 plus 14 gives me plus 11x cubed overall. I've got a single x squared, so minus 12x squared. A single linear term, so minus 7x. And then a single constant. So I'm going to tell you, these are the skills that you'll need to have as we move into this topic. Can polynomials be divided? The answer to that is yes, they can be, but we'll get there soon. So one of the big functions of this topic is polynomial division. But here is my last little point before I finish today, and that is that if two polynomials are equal, then their coefficients must be equal. And we can do something called equating coefficients. So I'm going to remind you in example 2 of a couple of important things that you've mostly seen before anyway. So let's just run through this very quickly. So A, we can evaluate polynomials if given a value. So A of 1 is equal to 2 times 1 to the power 6 minus 5 times 1 cubed plus 2 times 1 squared minus 1. And this is equal to, that's just 2, minus 5 is negative 3, plus 2 is negative 1, minus 1 gives me negative 2 in total. Again, always worth checking them. And then negative 2, A of negative 2, and this is where we substitute negative 2 in, but we have to be a bit more careful now because negative 2 is a bit trickier. So it's negative 2 to the power 6 minus 5 times negative 2 cubed plus 2 times negative 2 squared minus 1. And now I'm going to add an extra line of working here because I want to make sure I get this right. Negative 2 to the power 6 is positive 64 minus 5 times negative 2 cubed is negative 8 plus 2 times negative 2 squared is 2 times 4 and then minus 1. So that is 128. You probably pop it into your calculator now if that's the way we're working. Plus 40 plus 8 minus 1 is 168, 176, 175. So that's evaluating polynomials given a value of x, which will be important and will become much more important later in the year. And then part B, if b of negative 1 equals a of 1, what is the value of q? Now, of course, we've already evaluated a of 1. That's called evaluating a polynomial. But I'm going to do it again anyway, just to show you what this would look like in the long form. So I would write something over here like b of negative 1 equals a of 1. And then I'd put my evaluated polynomials there. So it's 7 to the power of negative 1. So 7 times negative 1 to the power 7 plus q times negative 1 to the power 6 plus 3 times negative 1 cubed is equal to, and now I can put in my a values here, which is 2 times 1 to the power 6 minus 5 times 1 to the power 3 plus 2 times 1 squared minus 1. And I'm going to evaluate this. So negative 1 to the power 7 is negative 1. This becomes negative 7 plus q. And this is 3, so that's negative 3 is equal to, and these values, we did it earlier, is negative 2. So I get q minus 10 equals negative 2, which means that q is equal to 8. And so I've solved for q, given some information about it. This is like hidden information, but it is there. So that's the kind of stuff I need you to do in exercise 8a. I've left a bit more space than I probably needed to, which is what I'll ask you to work on in this lesson. There's a mixed group of questions here. A couple of skills I haven't really talked about, but there's examples in the exercise to help you with that, that I'd like you to float through. I'm going to stop the video now, and so you can carry on with that.